All right, at some point in time, we were learning about derivatives, and like we started with a derivative rule for the exponential function, y is equal to e to the x. And we start with that because it's a nice, easy derivative rule, and it really kind of emphasized that this was a function, and the rate of change of this function is another function, and it happened to be itself. We then progressed and started to develop the chain rule, right? So what if my exponential function was slightly more complex rather than the input just being x? What if it was kx? We realized here that the derivative using the chain rule then just had that multiplier there. And then again, just using a slight change, y, wherever I see e to the kx, I can replace that with y. And this just brings a little bit general form to us. dy dx is k times y. So when we were learning derivatives, this statement, which right now I just want to see as this statement here, didn't really mean much more beyond that. They were just using the chain rule. But that statement right there is actually a pretty big model in our world. And that's what we're going to be talking about today. So in this box here, I have a bunch of words that you should read, but we've seen that, right? And this is what we did in our separation of variables video when we were solving differential equations. We were introducing that just so we knew that's why we were introducing that. But this rate of change, or this growth model, was always a continuous growth or decay original function. So in other words, what we're saying here is this rate of change was proportional to the original function. And that's our main understanding here. And that's what this section in our textbook is going to be working with. And then just some really important applications of. So make sure you're reading this box if you already haven't, and also making sure that when you hear the word proportional, you understand what that means. And take a quick moment now. I think I forgot to erase some ink here when I was thinking about what I wanted to say. So give me a moment to erase that. But just make sure you understand that we are only talking about continuous growth rates and not something else that we know, like what I might call like our more simple growth rate or like a discrete change. And that's what I have here in the back here. Like this was our simple exponential growth. Like we maybe think about that more with like algebra 1. Like we have a starting value and then a constant multiplier. Or maybe we could describe that as 1 plus or minus this rate of change, how many times we did it. But a lot of times, again, a constant multiplier, we have this idea of like how many times did you multiply? It's like a definitive or like a discrete type of amount change. So like just separating the distance here is like, let's say I have a bank account, I invest some money, and let's say it's going to take, or it's going to grow, I'm going to double my money every year. I have this like miraculous bank account. In our heads, it's easier for us to think about it as like a discrete change. 1 year has happened. But it's not like I have the step function of my bank account. It's not like all of all of 2020 I have this much, and then the instant the clock strike midnight, my bank interest goes up, right? What we're saying by that is if my account is growing, like doubling every year, it's really growing continuously. Like it's still changing throughout that entire year. Just at the ends of the year, it's at that right model where it's, hey, I'm double. So we're talking about continuous growth. That's kind of like our main idea here. And I just wanted to remind us of, we were introducing that as when we thought about where did E come from, right? We are growing money all the time, right? If I invest something into the bank, the number of times they pay me should give me more and more money, right? And that's what I want us to see here. As I increase the number of compounds, or in other words, the number of times I'm going to change my balance, I have more area under the curve. None versus twice. Now I have 3. So I'm getting more and more and more in area. And that's where we got to this. Well, I just want to always be compounding. And that's where E came from. It was that growth rate of continuous growth. The last thing I like about this is just making sure that we can understand that this is just a rectangle. I could say that rectangle represents $100 in the bank. I could say it represents $1 million in the bank. But everything is proportional, right? So this rectangle is a proportion of this rectangle. And this one's a proportion of that one because we're just taking percentages. So make sure we're only talking about continuous growth rates today. So the first type of example I want to go through, just so we can remind our separation of variables, and then we're going to be solving things fairly quickly with that method. So in this one, it says rabbits are living on an island, and it explicitly tells us that they are increasing at a continuous growth rate of 3%. So in other words, the change in their population with a small change in time, right? Continuous would mean all the time, every instant, their population is growing. Not every second, not every half second, every instant. And again, that's why we like to think about calculus as like a strategic use of infinity, right? An infinite number of time intervals, or as time approaches 0, the change in time approaches 0. So what we know then is it's proportional. So we're going to get 3% of whatever the population was. So when we were solving these, the separation of variables again, and this is the method that we're going to use every single time. So I'm going to solve these I might just say, and this is what we get after we solve it, just to save time, but using our separation of variables, we get this stuff on the same side. And then we would use integration. We get the natural log of the absolute value of p, is 0.03t plus, and here I'm going to call it C1 because I'm going to combine all the constant later. And then we have this idea of undoing the natural log by applying the base of e. And then like we had this reminder that if I saw addition in the exponents, it means I was originally multiplying common bases, and e to some number c1, that's just another constant, in which case I'm going to write c2 for this second. And now before I continue, I just want to take a moment to think about what we're saying about c1, or excuse me, c2. It could be anything because e to any number is anything. So we know that c2, this is just fancy symbols, belongs to the real numbers, but we know that it has to be positive because a positive number to an exponent has to stay positive. But then the idea when we were solving this is we know that this has to be positive because if I'm trying to equate it to an absolute value, this is always positive, and e to any number is always positive. So it forced this constant to be positive. So we made that little inherent restriction. But then to undo the absolute value, the way that we undo an absolute value is by including a plus or minus sign. And since this is always positive, if this could be positive or negative, the only thing that could change here would be this constant c2. But rather than leaving it as a plus or minus c2, here I restricted c2 to being a positive real number. If I include the negative, now it's just a real number. So rather than saying c2 is a positive real number and I can include the positive or negative of that, I'm just going to say c is a real number. So it could be any real number. So that's how we're handling those plus or minus signs. And I just chose c because it's more common to calculus. In a more of an applied state, we might choose that p naught because it better implies initial population. Once we have that model, we can simply plug it in. So if I started with 100 rabbits and I grew at this rate continuously for 10 years, I get 134, I'm just rounding 0.99. And just take a quick moment to compare that to a more simple growth model, just like that a times b to the x type thing. If it didn't grow continuously, if it grew annually at that rate, right, which is a different statement. An annual change at 3% versus a continuous change at 3% is different. Oops, a was 100. We can see that since it's growing less often, we have less rabbits. Now, I would also say that 100 rabbits and 10 years is not that long, so there's not a huge change, but we should see continuous growth over the same period as a simple growth should always be more. The last thing I do want to introduce you to is sometimes like 0.99 of a rabbit is weird. I'd prefer that you don't round up and just leave your decimals, which is why some way around that, some people choose or problems choose to talk about the mass of a population rather than the number of the population, because mass maps a little bit better to the real number values, whereas like rabbits, we tend to map to integer values. So continue with the decimals. So another straightforward application here, but I want to introduce you to the language here, right? So the rate of change. So they're describing a rate of change of a population as being directly proportional to something, right? And n of t is the population. So we can see the rate of change is directly proportional somehow to the original population. That is our indicator that we should be using our exponential growth model. And here we're writing it as a differential equation first because we're describing the rate of change of that population. So the rate of change is directly proportional. So now the way it's not what it's directly proportional to is 650 minus that population. And here is one level of complexity, but I'll explain that 650 in a moment. So it's directly proportional, that's what the k is, to this. So with that, we'd be using our separation of variables. And with this one, though, I would just warn you as a caution to watch out for that chain rule, because in this function, that n now has a negative in front of it. So like if you were thinking about, using substitution, if you let 650 minus n equal like u, let's say, -1 would be the rate of change. So dn would be replaced with -1 du. So when we start to use integration, that's where I'm going to get the -1 times the natural log of the absolute value of 650 minus n is going to equal kt plus c1. I'm going to get rid of the negative first. That's where we see all this change in the signs. So negative kt minus c1. And then from there, the solving of undoing the absolute value and the constants, all that good stuff, you can kind of work through that. So right now, we get to c times e to the negative kt. And then from there, we'd have to obviously isolate n. So our final equation would be 650 minus c times e to the negative kt. All right, so that's our general formula. Now with that general formula, we can then use information to get rid of letters. And I want you to see here we have too many letters, right? Our function notation, our dependent variable should be given if we give a variable of t. So we have to get rid of c and k for our function to work. So the first piece of information that they give us to use is the initial population, right? So the initial population should help me find c because k is part of the growth factor. And with no time passing, I have no idea of growth. So the population should be 300 when no growth has happened. So that's why, again, I really like you to tie that exponent of 0. So what we see here then, what if we subtract 300? We get 350 is equal to positive c. So then from there, we can just update our formula. And I think I'm just going to update it right here so I don't have to write too much. So this is 350. And then what we would do from there is we can then go back and use some passing of time to figure out growth. After 2 years, the population is 500. So the population should be 500. And on the right side, 2 years have passed. So we have e to the negative 2k. So then here what we're going to be doing is obviously solving for k. So we'd subtract 650 and divide by negative 350. We're going to take care of that kind of in one step and just represent that as a fraction, 3/7. So we would get e to the negative 2k is equal to 3/7. And then we use the natural log. So negative 2k is equal to the natural log of 3/7. And then divide. And then again, what I encourage you to do now, or maybe not again, but what I encourage you to do is when we are doing our math here, you need to show me the exact value of k. And what I mean by me is your grader, because when we're thinking about being assessed on like an AP exam or something like that, that's almost like a line in the grading manual. I need to see this. This is the answer. You need to leave it in exact form. But then you should also type it into your calculator. Once you can get an approximation of what that number is, and as we'll see in the next example, we'll want to be able to approximate those rates or something like that. But then also makes it a little bit easier to write, like if you had to kind of overall describe, like if I was going to come back up here and I was going to rewrite this. So the negative was already there, so just make sure we know that, but negative 0.423. And you could write that approximate version in like this final example. But again, the way that I want you to write your answer, include the exact, get a decimal approximation. And then whenever you're working with these, I'd always store it to something on your calculator in case you needed to calculate it. So then with that, that's our formula. So then we can use it to find the population when t is equal to 3. And at that point, I do want to quick kind of show you something in Desmos. So I'm going to call this f of x real fast so I can use function notation. So once I have that equation, like I could just plug in 3, right? It wants to know what is f of 3. So I can answer that question. It's about, so f of 3, or sorry, n of 3. In this case, I should have called it n on Desmos, my bad. But it's about 551.78. So that's great. But what I want us to point out here is this example was chosen as another preface, kind of like we did an example, a lesson ago to preface this one. There's an example here to preface the next one. You can see that general shape here clearly has a horizontal asymptote, and then that horizontal asymptote is at 650. And that's not a random number, right? See how that was in the formula. And what we're seeing here is just this kind of shape here. I wanted to include that, one, because it is a nice application. We kind of call this, you may have heard the idea of a carrying capacity. The idea of like population growth is those coyotes are going to run out of resources. They're going to run out of room. They're going to run out of something. So there is some limiting factor to their population growth. And then more so, that's also a little bit prefaced like our next lesson, I guess, is going to be on the logistic growth model. logistic kind of coming from logarithmic, right? And we kind of see that general idea here in population growth, that like the population is low, so the growth is low, but then as I start to get more people, my growth speeds up, and as my growth speeds up, I get more people, so my growth speeds up more. But then eventually we're going to reach that carrying capacity because we're going to run out of something. So with this one, this is another just a good example. So textbook prices have increased at 6.6%, and inflation has been increasing at 3.3% each year. And these are continuous growth rates. So I'm going to do A and C together and then B and C together because we just need to write and solve. So the change in the price of the textbooks with a small change in time is increasing at 6.6% of the original price every year continuously. Now with this, I'm just going to quickly solve that, and as we did in that very first example, take a moment to pause the video if you need to, but just using separation of variables, it's very formulaic in regards to like those steps are always the same over and over and over again. So using the separation of variables, you should have gotten the price of the textbooks is C1. I called it C1 because I'm going to be doing two equations, so I don't want to use C twice. C1 times E to the 0.067. Oh, sorry, 66, my bad. T. So price of the textbooks, and then we do the same thing with this price of the item of inflation. The change in price with a small respect, or the change in a small time, is 3.3% of that original price, continuously growing each year. So then again, by that same method that we've been doing for a while, we would see that that equation, I don't care if you use function notation or just kind of standard notation, would be some other C value. So that's why I'm calling it C2 e to the 0.033 times t. Right, now with this one, we're more looking at is kind of the relationship of the growth rates now. So what is the doubling time? And that's just another really good example. Like when we start dealing with exponential growth and decay, doubling time is a very common application. It's, analog or partner would be the idea of the half-life. And that comes in very handy in other things like we know, like radiocarbon dating. We use radiocarbon decay, a continuous decay model, to figure out how old something is. If I know how long it takes for you to cut your mass in half, if I know where you're at now, I can just go backwards, right? Or the same thing with doubling. Like if I invest something, I want to know like when I double, like rules of 7 and all that crazy stuff are kind of coming into play. But continuous growth and decay, half time and doubling time are very, very common applications. So we want to do one of those. So what's the doubling time of the price of the book? So with the price of the book, again, the formula that we had was C1, which we don't necessarily know because we don't know what that price started at in 1980, times E, and the book was growing at 6.6%, 0.066 T. Now the idea here that I like is it doesn't matter what the price of the book started at in 1980. If I wanted it to double, the growth rate is what's going to make that happen. That's because it's going to be proportional to the size. So when I divide by C1, it just goes away. So the growth rate here is what's really going to be affecting our doubling time. And I just kind of like that, that elegance there in that math here. So we'll use the natural log to undo this. And again, same thing with this. You would want to write the exact answer on your paper. But then since this is a measurement of time, I have no idea how many years the natural log of 2 divided by 0.066 is. So that's why then you'd want to approximate it. I'm just going to do 10.50. We'll do the same thing with the item growing at inflation. So that item started at some value in 1980. I don't know what it was though, but it's growing at 3.3% continuously. So if it doubled, I'd have twice of that value left. So we'll see that same math here. So again, we'll see the natural log of 2 over 0.033. We're going to see here, again, this is a rounded value of 21.0. And then this last question is just here to force us to like look at all these combinations of how nicely things worked out, right? The ratio of the doubling times is the reciprocal of the ratio of the growth rates. What I mean by that is I chose these numbers on purpose, right? 6.6% is twice as fast as 3.3%. Which is why it took half as long to double. So they're just getting us to see how nice some of these continuous growth rates are with that base of E, and that's why we're using that. And that's why it's just so nice. So they're just getting us to look at these growth rates. The last really important thing for today is going to be Newton's law of heating and cooling. So Like this is just a pretty straightforward idea. What happens to like beverages over time? So like on this, I have a temperature versus time graph, and that horizontal line is just the temperature of the room. If I start with hot coffee and I place it on the table in the room, and we're just going to assume the temperature of the room is constant, it's going to cool down, but eventually it's going to approach the temperature of the room. Like if I pour my coffee at 8 o'clock and I come back at 9 p.m., it's going to be exactly room temperature. Similar idea with a cold beverage. If I have ice water and then I leave it on my table, it's eventually going to be room temperature water. So one of the most important applications, Newton's law of heating and cooling. The change in temperature over time is proportional to the difference of the temperature of the object and its surroundings. So take a quick moment to internalize what this formula is trying to tell us. So the change in temperature over time. Let's think about our car and the speedometer. It's a numerical measurement of how fast my temp is changing. So we'll worry about K in a second, but let's just think about the idea. Let's take this basic example of an ice cube. So if I have, a little, that's my ice cube. If I have a little ice cube, and let's say for the sake of simplicity, because he's ice, he is 0 degrees Celsius. Now, again, I'm trying to just have a numerical measure for how fast my temperature is changing. Now, if I take that ice cube, which I know is already at 0 degrees Celsius, and I place it in an oven, let's say, and let's say that oven for simplicity is trying to boil water at 100 degrees Celsius. Now, 0 minus 100, without units or anything, just for the sake of simplicity, I want you to think of that as a really big number. That's a really big number, right? So if I'm thinking about the derivative as my speedometer, as a speedometer, a big number means big changes. You are moving really fast. And that would make sense, right? My ice cube should be melting really fast in the oven because the gradient or the temperature change between it and the environment is so high. Now compare that to something like if you're going to put it in a cooler. And maybe that cooler is at 20 degrees Celsius. Now when I look at the temperature difference, my ice cube is going to last longer because I want you to think about this as a smaller number. And if I'm thinking about a speedometer, a small number on my speedometer means I'm not changing very fast. That would make sense, right? My ice cube would melt slower in a cooler than it would in an oven. The very last kind of introduction to this topic, and we're not going through the full model. This is like a simplistic type idea. I mean, this is the model, but there's way more ways to be more exact. Is this proportionality constant? Let's think about coffee for a second. Let's say I have 100-degree coffee. Super hot. And let's say it's in a room that's 20 degrees Celsius. So the difference between my item and its environment is 80. So if I'm thinking about my speedometer, 80, that's a pretty big number, right? My coffee is going to cool pretty fast at room temperature. It doesn't take too long before I can drink my coffee. But there's other things at play here. Like for instance, if I put my coffee into a thermos, I would expect my coffee to cool slower. And that's what this K value is going to start to be. Think of it as like the heat transfer coefficient. That's just some other language, but it's just a modifier on this formula. My thermos should cause my coffee to slow down less. So maybe I'm just approximating. Maybe it's like something like 1/2. So now my speedometer is only reading 40, meaning I'm going slower. My temperature is changing at a slower rate. So it's going to take longer for that coffee to cool down, which is why we put it in thermoses. Now think about something else, like if I spill it. Well, if I spill it, imagine taking a super hot cup of coffee and spilling it over the entire kitchen table. You could almost immediately touch that coffee without burning yourself because it cools down so fast. So the gradient or the temperature gradient was already 80, but now in this case, the K value might be something crazy high, like 100, meaning, I'm just making all these things up. But now that speedometer is outrageously fast, meaning my temperature is changing so fast. And that's because it has such like a really big surface area. All the temperature can go down. And that's another way that this model is improved. Like this K value takes into the idea of like surface area over which the heat is transferring, all that good stuff. And this K value is inherent to the material. And that's what I want us to know moving forward, because one of our examples, we're going to assume it's material specific. So we have two examples with Newton's law of heating and cooling. First one, epic example here. Someone murdered Heidi with a candlestick in the dining room. A little ode to the game of Clue there. There's only 2 other people with access to the house, and they were her roommates, either Monica or Chris. We're trying to see who murdered her. We need to use the facts. And so it tells us Chris works at nights. So he wasn't home from, I should say 10 p.m. That makes sense. Sorry. He wasn't home from 10 p.m. to 7 a.m. And then Monica works during the day, so she left at 6:30 a.m. We have this information about like when she was found, the body temperature she had, and the room temperature. And then we have some reference ideas. And that's what I mean about this K value is material specific, like the heat exchange transfer for like steel, that's known, or how fast air exchanges heat, that's known. So those are things we would be able to reference. So we're using Newton's law of heating and cooling. So we'll start out with like the change in the temperature with respects to time is some proportionality constant times the difference in the temperatures. So for this example, we can start by saying we just got to use all this information, try to figure out who did it. We know the environment was 20 degrees. Right? So the idea here is we're going to come up with a general solution. And here's what I'm going to say the same thing. We're just using the separation of variables. Like as you're setting up that process, just pay attention. This one, the chain rule is not that bad. So when we're solving all of that, we should get like T is equal to, and again, if you need to pause the video, go ahead and do that. But again, that constant value times e to the kt, but then since it was t minus 20, we would have added 20 to get t alone. And again, same process, we've been doing that, so I'm saving time there. Now the idea here is we need to figure out this c value. And again, I want to figure out that c value first because I can get rid of t by setting it to 0. Now what that means is we got to figure out, like I said, we got to figure out like where would we start, right? So the idea here is a person's body temperature is normally 37 degrees. So Heidi's a person, so she would normally be at 37 degrees before she got murdered. So her temperature should have been 37 degrees 0 hours before she was murdered, right? So then we get this idea of 17 is equal to our value of c. But then what's next is we now need to figure out some idea of that coefficient, right? That K value. And as I mentioned, we're going to assume that this material specific. So the one way that one body cools is going to be like all bodies. So that's our reference here. So we know that it would take 2 hours to drop to 35, right? So now I'm using a passing of time so I can actually measure change. So it should help me find the K value. So her temperature should have been 35 degrees. And I'm plugging in 2 for the passing of time. And that would be 2K then, plus 20. So we're solving this like we get like 15 over 17 is equal to e to the 2K. So the natural log of 15/17 over 2 is the specific value of K, which you need to write on your paper. And then in this case, I know moving forward, we need it to do some calculations. So I'm going to approximate that now, negative 0.0625. So we can then fill out our kind of general formula per se, is that the temperature, given the passing of time, so how many hours since she was murdered, her body temperature after it stops producing heat, I guess is another thing to think about, is modeled by the 17E. And I'm going to use the approximation on my paper just so you know what I'm writing, but whenever I do a calculation, I'm obviously using the exact version. So this is our model. Now T, remember, is the passing of time since she was murdered. So this 4 p.m. thing is really the only thing we haven't used yet, right? 4 p.m. is the final time. T is hours since she was murdered. So we need to figure out, if we can figure out the passing of time, we can just go backwards that time from 4 p.m. So we'll use this last fact. So we found her body at 30 degrees Celsius. We're plugging in the model. And here I'm just going to write, again, the decimal approximation, but when I do calculations, I am using the exact value. So 10/17, and then on my paper I'd be okay of writing 10/17 divided by negative 0.0625 as my exact. So the natural log of 10/17 divided by negative 0. Divided by that. And here again, I'm using the exact value. It comes out to be 8.4789 is like an approximate rounded. Now T is hours since she was murdered. So let's go backwards, right? If we set up this timeline here, here's our timeline. This is 4 p.m., which I'm going to conveniently and more appropriately change to 1600 because it's easier to take away 8 hours, because 8 hours would be 8 a.m. I took away the 8 hours, but now 0.478 of an hour, that's like 28 minutes. Let's take away 28 minutes, so approximately 7:32 a.m. time of death. So I'm going for Chris, man. Because Monica left at 6:30 in the morning and Chris got home at 7. So Chris would have been the only person in the house with Heidi. So Chris did it. Let's all go get Chris. Last example. Really, you could feel free to pause and do it on your own. It's just an extra example. Nothing particularly new here. This is just, again, emphasizing that K value is specific to the material. So blood plasma, they take it from you and they like store it in a fridge, let's say. So they store it at 40 degrees, but before they use it, they got to heat it back up. So let's say we have this information that if we use an oven at 120 degrees, it's going to take 45 minutes. But maybe you're at a different hospital or something, and now our oven is only 100 degrees. So how long would it take? Because it's the same material, just in a different oven. So the idea here is the change in the temperature over the change in time should be proportional to the change or the difference in the temperature of the item and the environment. So the temperature that we know first is 120 degree oven. So again, using the separation of variables technique, again, that would be like your first step. Go ahead and do that if you're kind of working with me. Pause the video to do that. But we would solve that to get T is equal to some constant E to the KT plus 120. I'm going to call this C1 because I'm going to do another formula on the same page. I might use C again. So then from there, what we should do is, again, use our initial conditions. If it started, before I put it in the oven, if it started at 40 degrees and I didn't put it in the oven at all, this helped me figure out that my C value is negative 80. So in my model, and then I can go ahead and use my reference, right? My passing of time takes 45 minutes to warm to 90 degrees. And here we're going to assume that T is in minutes and not hours. I'm not going to convert. So this will be 45K. So when we solve this, we'd subtract 120 and then divide by negative 80. So it's simplified to negative 3/8 is equal to E to the 45K. So the natural log, negative 80. So this would be 3/8. So the natural log of 3/8 over 45 would be our K value. So the natural log of 3/8 divided by 45. So if we needed to approximate that, negative 0.0217. So again, I'm just going to rewrite that here then. So this is the model for that 120 degree oven. We can use that model now to know something about our 100 degree oven. And the main idea here is we could kind of start it the same way. I mean, we know that in this oven, the change in temperature with respect to the change in time is a proportion of the difference of the temperature of the item and its environment. So the same thing here is like when we'd solve this, we'd get back to this type of formula where we get T, and here I'm going to call it C2 just because it's a different oven, E to the KT plus 100. And again, with this blood plasma, before it's in the oven, the temperature would be 40 degrees. So it spent 0 time changing temperatures. So I can solve for C2. So then in my model, E to the KT plus 100. Now, with this one, what I want to figure out then is how long will it take to get to 90 degrees? But what we know now, this is the same material. So this K value is this K value. So I don't need to figure that out because it's the same substance. And again, that's what we're trying to say about that K value. So then from here, we can just go ahead and say, well, I'm not going to replace K because we know what it is already. I have it stored in my calculator. So I'm just going to say if the temperature was 90, and again, K is a specific thing, how much time has passed? So we get negative 10 over negative 60. I forgot my E, sorry. E to the KT. So 1/6 is equal to E to the KT. So the natural log of 1/6 divided by K should be our T. And again, by K, that's that specific value that we have stored on our calculator. And we get 82.20. So 82.205 minutes. So in that new oven, it's going to take 82 minutes to get there. So that's our application of differential equations with growth and decay. The stuff that's after this, as including your notes, the equilibrium stuff, we're just going to talk about in a different lesson because this has been long, but super important.